Hey guys, Ms. Marusik here, and in this video we're going to be looking at volatility and vapor pressure. Both are properties which are affected by the types of intermolecular forces that are present. So last class we looked a lot at melting points and boiling points and how those two properties can be affected by the type of IMF. You can add volatility and vapor pressure to that list. There's actually a few others on that list as well. For example, surface tension and capillary action, and if you're interested in those, you could look those up. But the only ones that AP Chem tends to ask about are melting points, boiling points, volatility, and vapor pressure. So if you're familiar with those four and they're tied to intermolecular forces, you should be in pretty good shape. So to start us off here with volatility, it says volatility is defined as the ease of evaporation of a liquid. Liquids that evaporate easily are said to be volatile liquids. Now think about that for a minute. If a liquid is evaporating easily, what that means is that it's not sticking together. It's willing to separate and come apart. And so as it's coming apart and evaporating, we would say that it's volatile. A substance that would rather stick together and not evaporate easily is said to be a non-volatile liquid. So think about how that would relate then to intermolecular forces. If I have very strong IMFs, what that means is that my molecules want to stick together. They're not going to separate and they're not going to evaporate. So if they're sticking together, then I should see a decrease in volatility. On the flip side, if my IMFs are weak, then I would have an increase in volatility. Weak IMFs would mean that my molecules separate very easily. So to kind of see this in action in an FRQ question, similar to what we did last class, this says that acetone is the main substance found in nail polish remover, which is known to evaporate very quickly. And it wants us to explain why acetone would be more volatile than water. If you've ever used nail polish remover, like on your fingernails or for whatever reason, you'll know if you leave the bottle open, almost half of it is gone within a day. Or if you're using it on your fingernails to remove the nail polish, it evaporates so quickly your fingernails are dry almost immediately, and you keep on having to re-wet your cotton ball that you're trying to use to get your nail polish off because it keeps on evaporating on you. So what we want to do is we want to figure out a reason why acetone evaporates so easily in comparison to water. So what we're going to do is we're going to compare the two structures to each other. Now they did us a solid here and gave us our structure for acetone. Hopefully we would be able to quickly draw a structure for water, basically in our sleep at this point, right? Hopefully we would be able to draw that no problem. And what I'm going to do is I'm going to first think about what kind of forces would hold these substances together as a solid and a liquid that eventually I would break as I'm transitioning to a gas. Now, both of these happen to be covalent substances. So I know I'm not going to be breaking bonds here. I'm not going to be breaking ionic or metallic or network covalent bonds. So that means I want to transition over to thinking about IMFs. Well, if they're both covalent, I know for sure I have London dispersion forces present. Now, because I'm going to be rewriting these forces in my actual statement, I'm going to just kind of put me some quick notes over here for right now. So I'm going to put that both of these would contain London dispersion forces. So there's my quick note about that. Next, I want to think about polarity. Are we going to have dipole-dipole forces present or not? So on this one, I see that the oxygen side of this molecule is very different than the carbon-hydrogen side of this molecule. And so bond dipoles here would not cancel out. And so therefore, I know that this is polar and would have dipole-dipole forces as well. Water, also very polar, as we know, so would also have dipole-dipole forces. So last but not least, I want to check for hydrogen bonding. Remember, to have hydrogen bonding forces between molecules, within the molecule, I have to have hydrogen bonded to nitrogen, oxygen, or fluorine. Okay, so I look here and I'm like, well, I have some hydrogens, but they're not bonded to nitrogen, oxygen, or fluorine here. And so therefore, acetone does not have the hydrogen bonding. However, as we know, water definitely does have that hydrogen bonding. And so I'm going to put HB here to remind me that it has that type. So kind of looking here, I'm like, well, golly, this water has an extra type of intermolecular force that this other compound doesn't have. And so when I'm going now to go write my FRQ answer, I might write something like this. So I put, first off, that acetone only has Lennon dispersion forces and dipole-dipole forces. Water, on the other hand, has Lennon dispersion, dipole-dipole, and hydrogen bonding forces. Notice that I've listed off all the types that are present in both of those substances. So now what I want to do is, after I've listed them off, I want to tie this back to strength of forces so I can argue the point of the question, the point that acetone is more volatile than water, which means it evaporates more easily. So looking at acetone, it says since acetone has weaker overall forces due to the lack of the hydrogen bonding, it's going to be easier to break those forces and evaporate. And if it's easier to evaporate, that would lead to a higher volatility. So notice that as I answered this FRQ question, I did some very set things. First, I identified the types of forces that are present. Then I kind of related one to the other. I said, hey, acetone has weaker forces because we don't have hydrogen bonding. And then I tied it back to the question I was trying to address. Why is acetone more volatile than water? I tied it back to that property. And so as we answer these questions in this unit, those are the kinds of steps that we would want to take in that process. All right, so there's volatility in a nutshell. How easily does it evaporate? Let's look at our other type of property here, which is vapor pressure. Now for vapor pressure, it is defined as the pressure exerted by gaseous molecules above the surface of a liquid. So basically, when I have a liquid that is just sitting, I'm going to have at least a few molecules at the surface that are going to have enough energy to evaporate off. Even though my substance might not be at the boiling point temperature, remember, temperature is a measure of average kinetic energy, kind of an overall average of molecule movement happening in that substance. So even though the bulk of my molecules might not have enough energy to vaporize, I'm going to have a few at the surface that do have sufficient energy. And so I'm always going to have some evaporation happening. Now what happens is, as that evaporation takes place, the gas pressure created by those vaporizing molecules is giving us our vapor pressure, which, by the way, we'll usually use this abbreviation PVAP to represent. So if you ever see PVAP, that's talking about vapor pressure. So now let's think about this again from the perspective of IMFs. If I'm again talking about evaporation, and the more evaporation that's taking place, the more gas molecules I'm getting, thereby creating a higher vapor pressure. All this evaporation and creating that higher vapor pressure means that my molecules aren't sticking together, they're separating apart. So if I'm getting that separating apart, I must have weak forces to get that evaporation to take place. So on the flip side of that, if I have strong intermolecular forces, that means my molecules would rather stick together. And if they're sticking together, it's going to take a lot more energy to get them to vaporize. They would rather stay together. So I'm not going to see as many of those molecules vaporizing, evaporating at the surface. And so therefore, strong IMFs would cause a decrease in vapor pressure at a particular temperature. We have to be careful here because there's actually two factors that affect vapor pressure. The type of IMF is one of them, but temperature also affects vapor pressure. We'll see a chart with that here in just a moment. So here's the deal. As temperature increases, the vapor pressure of a liquid will increase. And let's talk about why. Let's go ahead and flip the page and look at this table that's up here at the top. We see here that as our temperature continues to increase, the pressure exerted at the surface of a liquid, where our liquid is turning over into gas, would continually increase. But think about what temperature means. An increase in temperature means that those molecules have a greater kinetic energy. So if they have a greater kinetic energy, you're more likely to have more molecules that have sufficient energy to change over to a gas. So it makes sense that at these higher temperatures, I would continue to see that pressure increase. Now, by the way, this is a vapor pressure table for water. And you might notice that, first off, it ends at 5. Really, It doesn't go any lower than that, and it ends up here on the upper scale at 100. Well, think what happens outside of that range for water. At 5, below 5, as you get down to 0, you transition over to being a solid. So if you're a solid, you're going to have no evaporation. Everything's going to be solidifying, and you're not going to see that evaporation take place. So you notice the vapor pressure is really, really low there. Okay, on the flip side, over here at 100, if I am at sea level, at standard atmospheric pressure, that's the temperature at which water boils. And so if you notice, the pressure here is 760 millimeters of mercury, which is equivalent to 1 atmosphere, which is the standard pressure at sea level conditions. So what's happening here is that now everything is changing over to a gas, and so I wouldn't have any more values beyond that point. Now, if this data looks a little familiar, giving you a temperature and a particular pressure at that temperature, is because when we did gas law problems, we actually used this data when we calculated over water problems. Remember, over water problems, when I'm collecting a gas over water, we're always assuming that there's also a little bit of water vapor evaporating off the surface, and so we have to subtract these values from any pressure that's recorded over the water in order to make sure that we're only recording the pressure of the gas that I'm trying to collect. So if that at all sounded familiar, that was why. All right, by the way, it mentions here that full boiling of a substance occurs when the vapor pressure equals the current atmospheric pressure. When PATM, atmospheric pressure, equals the vapor pressure, that means boiling occurs. We've got to get all of that gas to form from that liquid if we're fully boiling. If we're less than boiling, only the surface molecules are vaporizing. So that's your big difference there. Is the whole substance boiling off and changing to a gas, or is it just the surface? That's the big difference between evaporation and boiling. Evaporation is surface, boiling is the whole substance. Now, something interesting. If I have some sort of closed container situation, we get an interesting phenomenon to take place. So when I close the container and put a liquid in it, what happens is that we start to get some evaporation to happen. But at some point, we reach a particular pressure in that container. And so at some point, once you've reached that pressure, some of those molecules are transferring energy between them, like say to the container itself or to each other. And so some of those molecules start to lose energy as well. And so eventually what will happen is you'll start to see condensation start back up. And so once those two have equalized out, where eventually the vaporization rate equals the condensation rate, we can reach what is called a phase equilibrium, where the rate of vaporization and condensation will be equal if I have a closed container. By the way, when this happens, what that means is that the pressure inside of this container is the vapor pressure. So that is kind of part of the definition of vapor pressure, is if I had a closed container, what would that pressure end up being that's created from that gas coming off the surface of the liquid? By the way, to kind of give us a wordy explanation of what happens here. So to start us off, here we have flask A. You notice they put a liquid in here, they sealed it up, and it says when you first put a liquid into that closed container, the pressure of the flask is less than the vapor pressure standard at that temperature. So like, let's say, for example, we had water here, and let's say, I don't know, we're at 25 degrees Celsius. If I come up here, I see, hey, at 25 degrees Celsius, I should have a pressure of 23.8. Well, right now, I don't have that pressure coming from the gas. I don't have that 23.8 yet. But eventually, if I let this sit long enough and allow the vaporization to happen and let it reach the point where then condensation starts to happen, where again, those two rates equal out, then eventually what will happen is the condensation and vaporization rates will equal out, and the pressure in the flask ends up equaling the vapor pressure that's standard at those conditions. By the way, if you've ever left like a little bit of water in a water bottle, and let it sit like, for a couple days, like on a countertop or something, and you've ever noticed like the water droplets kind of sitting on the surface inside of the container, what has happened there is you've reached this idea of phase equilibrium, where the pressure of the flask and the pressure of the vapor are equal to each other, because what that means is that your condensation is occurring on the outside. Remember, condensation doesn't have to happen on the surface of this. It could happen anywhere in that container. One last thing I want to mention here that's kind of important about this. Notice that in every situation I've talked about here, your container is always closed. The reason why is if your container is open, eventually as that vaporization starts to take place, your liquid turning into a gas is just going to leave. It's never going to be available to turn back into a liquid, and so you'll never reach that phase equilibrium point. So it is important to have a closed container here. All right, let's go ahead and look at the next page and see some examples with this. So it asks us here, would acetone left or propanol right be predicted to have a higher vapor pressure, 25 degrees Celsius? Justify your decision. Well, as we said a little while ago, our acetone has both London dispersion forces in it, and it also has dipole-dipole forces in it. That's from earlier, okay? They give us another substance here, propanol. We see it is covalent. It's not ionic or metallic or anything like that. So we know we don't have bonds involved. We're going to have IMFs involved. Since it's covalent, we know we're going to have London dispersion forces here. We can see that it's polar because we have this OH over here on the side. That would make it unsymmetrical. And then I see, I do have oxygen bonded to hydrogen. I have our special bond in here that would end up creating intermolecular forces of hydrogen bonding with other molecules. So this one does have hydrogen bonding. So a very similar situation to what we saw earlier with the acetone and the water. So if I was predicting here which would have a higher vapor pressure, here's the kind of thing I might say in an FRQ answer. First off, I would mention both the types of intermolecular forces that we have present. Acetone has London dispersion forces and dipole-dipole forces. Our propanol has London dispersion, dipole-dipole, and hydrogen bonding forces. So, here's the deal. If I'm trying to think about which one would have a higher vapor pressure, I'm looking for one that's going to evaporate easily, meaning I'm looking for the weaker forces. So, since acetone has weaker overall forces, again, because it doesn't have that hydrogen bonding, it's going to be easier to break those forces and evaporate, so the more gas I'm producing would lead to a higher vapor pressure than the propanol, the other substance. So again, kind of a similar justification that we saw for volatility. It's just now we're talking about the pressure of the gas versus just simply the ease of evaporation. All right, so on the next one here, it says, hey, would liquid hexane or liquid octane be predicted to have a higher vapor pressure at 25 degrees Celsius? Justify your decision. Now, I kind of went ahead and gave a loose sketch here of both the hexane and the octane. Keep in mind that at each of these bonds, there would have also been hydrogens there. I didn't take the time to draw all of those. But I'll be honest with you, I could have actually predicted some types here before I even drew these, and let me explain why. First off, I see that they're both covalent, so I know that IMFs are going to be involved and not bonds. It's not ionic or metallic or network covalent. And so I know that both of these would have London dispersion forces involved since they're both covalent. So then I'm going to ask myself, well, do we have dipole-dipole? Are these molecules polar? Now remember, something that we talked about last unit is the fact that if I just have carbons and hydrogens, that's all that's in the substance. There's none of those organic functional groups like alcohols and esters and ethers and all kinds of weird stuff. Then what that means is that these are nonpolar. So even without drawing these, just noticing that they were only carbons and hydrogens, I should have been able to pick up that they were nonpolar, meaning London dispersion forces are my only type here. So that's kind of a problem because that means I can't use type of IMF to justify here. So now, here's where I have to kind of go back to what we talked about last class and ask myself, well, what could cause differences in London dispersion forces? Well, there's two things. Thing number one is branching. If one had more branching, it would have less surface area and it would be less polarizable. But remember, the other thing is the number of total electrons. Okay, if I'm comparing these two, liquid octane has more stuff in it. Oops, I forgot two bonds there. And so having more stuff in it means that we would have more electrons. Here, this guy would have less electrons. Okay, so here's kind of the thing I would write. And I bet a lot of you can think about where this is going if we're talking about electron counts. So I put the statement that both hexane and octane contain only London dispersion forces, but hexane has less total electrons. If it has less total electrons, that leads to a less polarizable electron cloud, our new fancy P word, polarizable. And so if we have a less polarizable electron cloud, there's less chance of those temporary dipoles happening. So we have decreased temporary dipole moments and thereby weaker London dispersion forces. And if I have weaker forces, then that means hexane will be easier to break forces and evaporate. And so it should have the higher vapor pressure in comparison to the octane. All right, one last thing that we can also do when we're talking about comparing vapor pressures is that we can address why at different elevations we see different boiling points. I would hope that most of us are familiar with the fact that the normal boiling point of water is 100 degrees Celsius when I'm at 1 atmosphere of pressure. That's kind of the standard that we're used to. But what some people don't realize is that the boiling point can vary depending on your altitude. If you've ever paid attention to like the back of things that you bake or things that you cook, like noodles or brownies or cookies, if you have some sort of cake mix, it'll have on there different times for people that are at higher elevations. Like let's say you lived in Denver, Colorado, which is a mile above sea level. Things cook and boil at different temperatures there, and so that can cause our cooking times to decrease. So to kind of see this in action, it says, hey, what happens if you're at a higher altitude, such as on a mountain? What happens to our atmospheric pressure? Well, if you're at sea level down here, that is the standard of 100 degrees Celsius for our boiling point. And at that point, your atmospheric pressure, the pressure of the air, is 1 atmosphere. However, if you go to the top of a mountain, the pressure of the air is much less than 1 atmosphere. You don't have as much atmosphere above you. If you've ever been to the top of a mountain and you've tried to breathe, like if you've gone hiking in the mountains and you try to breathe, you always have a really difficult time breathing because the air is so thin up there because of that low pressure. So that affects our boiling point. We're going to talk more about that here in a hot second. On the flip side here, let's say you're in some sort of valley area. That would cause a pressure that is greater than 1 atmosphere for the air. Now, let's think about this for a minute. If I am trying to justify why something boils at a particular temperature, remember that to boil, you have to get the pressure of the gas coming off the surface of your liquid to equal the pressure of the air. And so with that said, I've kind of put a justification here that you can use for both of these. It says, since boiling happens for a substance when the vapor pressure equals the air pressure, if the air pressure is decreased, like say on a mountain, the vapor pressure does not have to get as high to boil. So what that means is that you can end up boiling at lower temperatures on a mountain because you don't have to get as hot in order to get that gas to evaporate off. It'll evaporate off at a much lower temperature. There's some interesting videos on YouTube of people that have tried to boil things, like boil water, as they're climbing through the Mount Everest base camps. And the last base camp that they get to, it's not quite at the top of Mount Everest, but you're within several thousand feet of that last checkpoint. And what they figured out is at the last checkpoint before you get to the top, the boiling point of water there is about 85 degrees Celsius instead of the 100 degrees Celsius. Why? The atmospheric pressure is so low that it doesn't take a lot of energy to be able to escape off the surface of that liquid. There's not as much pressure from the air pressing down, so your gas from the liquid can escape a lot more easily. So it's actually a really interesting phenomenon that most people don't think about. And that's why, again, if you look at, boxes where you're cooking things and making cake mixes and whatever, they'll actually give you different baking times and different baking temperatures, depending on your altitude. All right, one last question that I want to talk about on the next page. They give us a lovely chart here that says, hey, which of the substances in the graph shown to the right has the weakest intermolecular forces? So what this chart is it's showing us various vapor pressure values, okay, and temperatures for particular substances. So as we can see, for each of these substances, as the temperature increases, as we start to get more and more energy to those molecules and the evaporation is happening more easily, the vapor pressure would increase. However, what they're wanting us to do is to state which of these substances, so diethyl ether, ethyl alcohol, water, or ethylene glycol, which of those substances would have the weakest intermolecular forces. Now, there's two ways we could evaluate this graph. Way number one is that we could look, hey, what's got the lowest normal boiling point? Obviously, if it has the lowest boiling point, that would indicate the weakest forces. So looking on here, notice this 760 torr, which is equivalent to 1 atmosphere. Wherever temperature those are crossing over, that is where we would have our normal boiling point. So you can notice here for water, that's crossing at 100 degrees Celsius. However, for diethyl ether over here, that's crossing at only 34.6. So it looks like that's going to be our winner. But the other way that you could read this graph is you could look and say, hey, at a particular temperature, which one has the highest vapor pressure? If the vapor pressure is the highest, then that would mean that the bulk of it has transitioned over to a gas, and so you must have really weak forces. So like, let's say I just randomly pick, 20 degrees Celsius or 40 degrees Celsius, somewhere in here, and I look, hey, which of these has the highest vapor pressure at that temperature? I can see that all these graphs would be really low, but diethyl ether here would be really high at those temperatures. And so what that means is the bulk of it is transitioning to a gas, and so therefore it would have the weakest intermolecular forces. All right, hopefully we're feeling pretty confident with being able to reason out volatility and vapor pressure. If you have any questions or need any help, please feel free to email me. Bye, guys.